Let V be the velocity field. Compute the outward flux of V across the surface of the solid bounded by x squared plus y squared plus z squared equals 25 and x equals 0. So looking at the graph on the right, x squared plus y squared plus z squared equals 25 is the sphere, x equals 0 is the yz plane. So we're looking for the outward flux across the surface of half of the sphere and the circle where the plane intersects the sphere. And since we're looking for the outward flux across the entire surface of the solid, we can apply the divergence theorem. Let's review the divergence theorem. The divergence theorem involves the flux of a vector field across a surface in space. This theorem states the total divergence of a vector field in a solid region V equals the total flow across the boundary surface S. So V must be a solid region bounded by S, oriented by a unit normal vector directed outward. The partial derivatives must be continuous. So if these conditions are met, then the flux integral across the surface is equal to the triple integral over the solid region V of the divergence of the vector field, where the divergence of the vector field is equal to the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z, where f, g, and h are the x, y, and z components of the vector field. This shows a relationship between a triple integral over a solid region and the surface integral over a surface. This theorem is a 3D version of the flux form of Green's theorem. So going back to our example, let's begin by determining the divergence of the given vector field, where f is equal to the x component of x squared z, g is equal to the y component of 5 minus 2xyz minus 3y plus x squared y, and h is equal to the z component of 3z minus x squared z. Before we set up the triple integral, let's find the divergence of the vector field V. Which is equal to the partial of f with respect to x, which is the derivative of x squared z with respect to x, treating z as a constant, which is 2xz. And then we have plus the partial of g with respect to y. So now we differentiate g with respect to y, treating x and z as constants. The derivative of 5 with respect to y is 0. The derivative of negative 2xyz with respect to y, treating x and z as constants, would be negative 2xz. Let's write that as minus 2xz. Minus the derivative of 3y with respect to y, which is 3, plus the derivative of x squared y with respect to y, treating x as a constant, which gives us plus x squared. And then we have plus the partial of h with respect to z. So now we differentiate 3z minus x squared z with respect to z, treating x as a constant. The derivative of 3z with respect to z is 3, and minus the derivative of x squared z with respect to z, which is x squared. Simplifying, we have 2xz minus 2xz, negative 3 plus 3, and x squared minus x squared. The divergence of the vector field V is equal to 0, which means the outward flux is equal to the triple integral over the solid region V of 0 dV, which of course is equal to 0. So if we think about this for a moment, notice how there are two surfaces for the solid. There's the half sphere or hemisphere, and then the circle. And since there are two surfaces and the outward flux is 0, we know the flux across the two surfaces must be equal but in the opposite direction, resulting in an outward flux as well as an inward flux of 0. I hope you found this helpful.